So continuing from what we were doing, and we were talking about the inertia and the first law of Newton, which is also known as the law of inertia. And I told you that the inertia is, in a way, it is indicated by the amount of matter that the body has. The amount of matter that the body has, that is defined as the mass of the object, the mass of the body. So if the body is more massy, then it has more inertia, and if it is lighter in mass, its inertia is said to be less. But we need to understand that in terms of an experiment that was conducted by Galileo, and that is, he takes a tumbler here, and on the tumbler he puts a card, and on that card he puts a heavy coin. And what he does is that he flips the card like this. When the card is flipped like this thing is explained in books vividly. So what happens that if you flip it like this, then the situation is that the card flies away, it is flicked away, but the coin on the card, it drops into the glass as if it were not on the card. And of course, before it is done, the flipping thing is done here, what happens is that this is experiencing two forces, at least a pair of forces. One is the force which is due to the gravitation of the earth, and other is the force which is due to the reaction of the card. And I told you that the two forces are equal and opposite to each other, as is evident here. So what happens is that when this action is finished, then this drops into the glass. So I am not making that diagram for you. I am only saying that the massive objects possess more inertia than the lighter objects. And the inertia is of two kinds. Inertia of rest. This is the case of inertia of rest. And an example of the inertia of rest is the coin sitting on the card. Okay. Another is, if I am a passenger on a bus and the bus suddenly starts. Now my feet are on the board of the bus, my body is on the board of the bus, and when suddenly starts the bus, then what happens? I go back, fall back. So if there is nothing to hold, then I will fall. The second example of the inertia of rest is that if there is a tree laden with ripe fruits and I hold a branch and then we just give it a jerky motion, and what happens is that the ripe fruits, they drop down due to their inertia of rest. And then I'll talk to you another inertia of motion. Inertia of motion. if a body is moving, and I told you that inertia stays in the case of rest as of uniform motion. Okay, so in that case we have, the example is that if I am in a bus and I'm moving with a constant speed in the direction the bus is moving, my feet are on the board, and then suddenly the bus is made to stop. During that retardation, when the bus stops, then I again fall. Which direction we will fall? Okay, in the opposite direction again. Okay, in the forward direction. Okay. So, and there is another example, that suppose I am on board of a train or a moving bus which is moving with uniform speed in the same direction, that is the case of uniform velocity, and if I throw a ball, if I throw my ball, then will it be possible for the ball to come back to my hand? Because from the same spot where I am doing it, I am pushing up, my body is moving in the bus, but there is, while this motion goes, there is the motion associated with the ball also, and that motion also is in the same direction in which the bus is moving. So in that case the bus will fall, and it will fall in my hand, in your hand. Okay, so this is the inertia of motion.
The ball will fall.
So the law of inertia says, is the same. The law of inertia says that every body continues to be in its initial state of rest or of uniform motion in a straight line. Okay, it is stated like that, the law, until and unless it is a force is exerted upon it by some external agency sufficient to change the state of rest or of uniform motion. So this is about the thing. Now I told you, and first of all, before going to the second law, Newton's second law, I will discuss the concept of momentum, which I told you that in most of the languages the concept of momentum does not exist in because there is a tendency to translate it. Okay, of course, in an old language like Arabic we have the understanding of what momentum is about, but in Hindustani, as I told you, that there is word, and that word describes this momentum, which we represent by the letter P, which is the vector quantity, and is given as the mass into the velocity. The mass into the velocity. This is a scalar and this is a vector, and I have told you before that a scalar can be multiplied by a vector and we get a quantity like that. Now in our language of northern India, the Hindustani language, what you can say Hindi, what you can say Bhojpuri, what you can say Awadhi, Braj or Urdu, whatever, there is something called jhonk. So what happened? I was going in my jhonk and I fell down. The vehicle was coming with its jhonk, and that jhonk signifies a motion associated with it, with the mass of the body intact. So the jhonk is there, and we say that this P is equal to mv. Okay, so here in both the cases, in the case of rest, what is there? The velocity is equal to 0. In the case of uniform motion, the velocity is non-zero. Okay, so but in both the cases, if I have the body of mass m, and I'm just picking up a round shaped body, it has got a mass m and it has got a velocity equal to 0. So the momentum associated with this will be equal to 0. Okay, the momentum associated with uniform motion, I take it as the rigid body, the momentum associated with the uniform motion, and the motion is there, and here we see that the velocity, I can say, is greater than 0. Okay, the mass exists, the momentum exists. Okay, and in this case or the other case, in both cases, because there is no acceleration, therefore the force here is equal to 0 and the force here also is equal to 0. Because there is no acceleration, then in both cases the force is equal to 0. Okay, so I can say that there exists a system in which we can say that there are two particles, one where the momentum is equal to P1, which is equal to the mass of the body m1 multiplied by its velocity v1. Okay, and there is another one where the momentum is, the magnitude of the momentum I am taking over here, the mod of it m2 into v1. Now let us compare. If we compare these two, I can say that left hand side P1, suppose divided by P2, this is equal to m1 v1 divided by m2 v2. And suppose if P1 is equal to P2, then m1 v1 will become equal to m2 v2. But if P1 is larger than P2, then we find that m1 v1 is larger than m2 v2. Okay, so I can write if P1 is equal to P2, m1 v1 is equal to m2 v2. If this is larger than this one, then this whole quantity will be larger in the same proportion to m2 v2, and therefore we can find out that in the first case we find that if the mass is less, then the velocity will be more, so that the product becomes equal to P1, and mass is less than, I'm sorry, if the mass is more, then the velocity will compensate for it. Okay, so with that we come to sort of, I have introduced, now I have left something that you do some numerical examples and try to understand what it means. Okay, so now I come to Newton's second law of motion. And Newton's second law of motion I define, and the old definition is from the olden days. When I say about it, I remember always my book Basu and Chatterjee. Okay, and that used to be one of the finest books at that level. It was basically written as a help book, but later on it became a textbook. Okay, so going by that, we can just say that we are going to define Newton's second law, and it's very simple. But it could not be obtained so easily. But the Newton's first law is defined, second law is defined as the force is proportional to the rate of change, time rate of change of momentum. And if I take this as vector quantity, the force also got to be a vector quantity, where P, the momentum, is equal to mass, which is an invariant over here, into the velocity. Okay. So the second law can be defined as the force is proportional to the rate of change of momentum. Also, if I use this equation, then we get this. Suppose F is equal to, I write some constant times k times d dt of the associated momentum with the system of particles which we are studying, okay, dp dt. So force is equal to k dp dt. I can write this as k ddt, rate of change of time, rate of change of m into a. Okay, where k is the constant of the system which we have to determine. As I told you, that it is determined by the constraints of the system, by the boundary conditions, etc. that we have. So I'll write this as, now there is something which is required. We must know that ddx of the product of two functions, f1x and f2x, which our mathematics teacher says that the product of these two will be equal to, and I read it in words, that the first function into the ddt of the second function, ddx of function 2x plus, look here, I'm going to write ddx of function 1x into function 2x. Okay, what I'm writing, so I have this as a product of two functions. The differential is first function into the differential of second function plus differential of first function into the second function. Some of the mathematics teachers, they don't care. They don't care the order. My order is the product here. The product here is f1x into f2x. So f1x exists first and f2x exists next. So what happens is, if I take like this, function 1 ddx of function 2 plus ddx of function 1 into function 2. That is in words what I am taking here. But sometimes what they do is that our brethren in mathematics, they don't care about the order, and what they say is function 1x ddx of function 2x, and this they bring here, function 2x into ddx of function 1x. That's wrong. That's wrong. That they should not do. Why? Because sometimes we students, we don't know what kind of a product is this. if this is a simple algebraic product, or sometimes it could be the function 1 cross function 2x. If the cross product is there and we apply the same logic of mathematics of function 1x ddx of function 2x plus function 2x into ddx of function 1x, then the results will be horrible. Okay. However, one thing I can say to you, that this hole here and this hole here, they can commute. They can commute, there is no problem in that. But what should be taken into consideration always, as I said, that function 1x should be first and then function 2x, ddx of function 2x plus first function into the second function. So if I apply that, oh, I'm sorry, I'm very sorry, there should be a V over here. Okay, I'm very sorry, sometimes it happens because I'm very close to the board. Okay, I have to stay close to the board in the setup that I have with its constraints. Now I would like you to write, according to this there is a product of two things, and I can write this that f is equal to k times first function m into the ddt of the second function ddt of v. K I am taking as common plus the ddt of the first function ddt of the first function, which is m into v. So dm dt I can write it like this, and dv dt I can write like this. Now you understand that the product mv has been taken into consideration, and I write it like this. Now m, you may be asking me a question, why are you taking m as variable? It's a constant. Okay, so I'm just trying to indicate to you that m is a function of the velocity of a body. In the special theory of relativity, the mass at a given velocity is the mass at a given velocity v is equal to something called the rest mass 1 minus v square upon c square, where c is the velocity of light, 10 to the power of 8 meters per second. Okay, normally the velocities that we are dealing at this stage, they are very, very small as compared to c. So square this quantity approximately becomes equal to 0, and I can say that my m I can write is approximately equal to the mass, rest mass, okay, which I will write as m, and which I'll say that here in the case that we are describing is not a function of time. Okay, it's not a function of time. And if so, then dm dt becomes equal to 0. And if dm dt becomes equal to 0, then I can write this expression as k m dv dt plus 0. Why? As dm dt is taken as equal to 0. So now we are sure that the velocity is being small as compared to the velocity of light, which is 10 to the power of 8 meter per second. This is the value of C, and you know, I just remind to you that the sun is so far away from the earth that it takes about the light is starting from the sun, reaching the earth at any given time. If you say that this is that time is 10 seconds, then the light is started at a time 2 seconds, and it reached the earth in 8 I'm sorry, it's not seconds, it's minutes. It takes about 500 seconds to reach from here. And if I have a torch and I put the torch towards the sun, then the light, the photons emitted out, they may travel for about 8 minutes and reach the surface of our information can reach there 8 minutes after the information we project from our torch, the data that we project from our torch, or any electromagnetic radiation that we do from the torch. So if that, then what I get is, I can write my expression therefore that my F is equal to K M dV dt, which is nothing but the acceleration, the associated acceleration, which is K M into A. Give it a thought. And of course we'll choose the value of K, and our choice for the value of K will be to choose K such that the value of K turns out to be equal to 1. In fact, what we are going to do is, we are going to choose the unit for F in such a manner that if this is 1, M is 1, yani kilogram, we know that the unit is kilogram, and A, which is meter per second square in the SI system of units, then we choose our K to be equal to 1. So if K is equal to 1, I'm just giving you in a fast manner, so my F turns out to be equal to MA. MA taken as K is equal to 1, and the unit associated with the force. This equation is right or wrong? This equation is absolutely wrong. The equation is absolutely wrong. I'll make it right, because left hand side and right hand side both should be vectors. Okay, so if I make that mistake, that should not be there. So force is equal to mass into acceleration, as also from the definition is that the force is equal to, then it turns out to be F is equal to dP dt, or I can write my F is equal to ddt of P. P, and P has also to be a vector quantity, so it is dP dt. Okay, so the force is defined in the Newton's second law. Now we can see that if we choose the value of F to be equal to 0, like we do, like I explained in the first law, that it simply says, in the absence of a force, the body at rest will remain at rest, the body in motion will remain in motion, that is, there will not be any change. So if this is taken as equal to 0, then this becomes equal to 0 whole thing. That means, and ddt of what is equal to 0? ddx of what is equal to 0? ddy of what is equal to 0? It's always a constant, a constant, a constant. So that means there is no variation in the value of P. As I told you there. So inherent in the second law, the definition of the second law, definition of the force, there is the first law which is hidden. We can say the first law is hidden in the second law. Okay. Now, I will take one more lecture to explain to you, but right now what I am going to tell you is a little indication about the third law. And the third law had to be there. Third law had to be there because the second law and first law together, they are not able to explain the motion of a body. Well, how come this third law come into being? Suppose there is a body which is at rest, or there is a body which is moving with a constant velocity. Of course, in both cases, no force is required. And if no force is required, then this body in the state of rest or of uniform motion can exist all by itself in the space time continuum without the presence of any other body. So the force is there, but what is the source of the force? So if this force is not equal to 0, it means that there has to be a second body. There has to be at least a second body. And this is how Newton explained. I'll just wind up by giving you the definition of the commonly known definition of the third law. To every action, there is an equal and opposite reaction. To every action, there is an equal and opposite reaction. The two words, one word is action and the other word is reaction. And in English, in Hindi, in any language, in any European language, if you ask the person that to every action there is an equal and opposite reaction, and which precedes the other, which occurs first, which occurs second, then the people will say that, well, action has to be taken at a given time and the reaction will follow. That means the time of start of reaction is different from the time of start of action. We'll talk more about it and we'll see that the action and reaction is a pair of forces which act on different bodies. And I will tell you a very interesting law which did not appear in the Principia Mathematica. What is Principia Mathematica? It is the book that was written by Newton. When a few hundred years after that, towards the end of the last century, one of the crazy students of physics, a professor from a university in United States of America, he visited the archives of Newton, because the Newton's room is sealed, and he paid a lot of money, both secretly under the table and of course over the table, and he was monitored and this and that, and he was made to stay in that room of Newton. So of the many other revelations which I'll not tell you, one of the things was that while discussing the page on which the third law was written, Newton wrote that the state of a body is determined by the forces acting on the body and not by the forces which the body exerts on other bodies. He thought that he should have included this, but about the action and reaction. About the action and reaction, in 1980s, there was a proposal to make understand the action and reaction, make students understand that reaction does not follow action. There was a movement, and it was said, the statement was made, to every interaction there is equal and opposite interaction. I will elaborate that for you, and I request you, I urge upon you to read whatever book you have, okay, about this second law, so that we can enjoy the third law more details with all the gravity that is there. Okay, so see you in the next lecture. Bye.